Hi, my name is Ashwani Kumar. In this video, we are going to see this problem is a GATE 2019 problem. See here, look at this question. In this circuit shown, the breakdown voltage and maximum current of the Zener diode is 20 volts and 60 milliamperes. Okay, so here 20 volts is the VZ, that is the breakdown voltage of a Zener diode, and 60 milliamperes is the maximum current of the Zener diode. Next, the values of R1 and RL are 200 ohms and 1 kilo ohm. So what it means is that here RL is 1 kilo ohm and R1 is 200 ohms. What is the range of VI that will maintain the Zener diode in the on state? That means we have to find out the range of VI. Range of VI means VA minimum we have to find out, and VI max we have to find out. That means what is the minimum voltage to make the Zener diode in on state, and what is the maximum voltage is required to make the Zener diode in the on state. So before going into the solution of this problem, first let us focus some time on the Zener diode. Okay. So while coming to the Zener diode, see Zener. So he is an American scientist who invented the Zener diode. So Zener diode is different with respect to the conventional PN junction diode. What is the difference is that while coming to the conventional PN junction diode, the doping concentration is different, and while coming to the Zener diode, the doping concentration is high comparing with the PN junction diode. So in Zener diode, the doping concentration ratio is 1 is to 10 power 5. So it is a doping concentration ratio of the Zener diode. So what it means is that for every 10 to the power of 5 intrinsic semiconductor atoms, we are going to dope one impurity atom. Okay, so it is the meaning of this 1 is to 10 power 5. And while coming to the Zener diode, we are going to represent the Zener diode like this. Okay, this Z. Okay, it is a Z type of structure, which is the first alphabet of the scientist name. So the Zener diode, equivalents can be taken into the three formats. The first one is the Zener diode may be short circuited, and the second one is the Zener diode may be open circuited, and the third one is the Zener diode is acting like a voltage source with voltage Vz, that is a breakdown voltage. So these are the three different equivalents we can able to take to the Zener diode. But on what basis we have to take these equivalents? Here we are going to say that if a Zener diode is forward biased, then it just acts like a conventional PN junction diode. That means it simply short circuits. Next, both these two cases are for the Zener diode in reverse bias condition. Okay, so if the Zener diode is in reverse bias condition, then the Zener diode may act like an open circuit, and it may act like a voltage source with the capacity Vz. Okay, so when they are going to act like this open circuit means, if I took a Zener diode like this in a circuit, it is a voltage source I connected here. It is a positive and it is negative. So positive is going to the N type of the Zener diode, and negative is going to the P type of the Zener diode. That means the Zener diode is in the reverse bias condition. So if here the input is Vi and Vz is the breakdown voltage of the Zener diode, then this equivalent circuit will happens whenever the Vi is less than Vz. That means the input voltage is less than the breakdown voltage of the Zener diode. Then it simply acts like a open circuit. Next, the second case of the reverse biasing condition is here the Zener diode is acting like a battery with voltage source of Vz. So when it is going to act like that means if input voltage is greater than breakdown voltage. Okay. The input voltage is greater than breakdown voltage, then the Zener diode acts like a battery with capacity Vz. Okay. So total these are the three equivalents and it is a condition for the forward bias condition. Okay. Forward bias condition means N type has to be connected to the negative polarity of the battery and P type has to be connected to the positive polarity of the battery. Then it becomes like a, when it acts like a forward biased, in the forward bias condition of a Zener diode, it simply acts like a forward bias condition of a conventional p-n junction diode. Next, if a Zener diode is reverse biased like this, that means positive is connected to the N type of the diode and negative is connected to the P type of the diode, then there is a chance of acting in both these two equivalents. But when it acts like this open circuit means if the input voltage is less than Vz, then the Zener diode acts like an open circuit. If the input voltage is greater than Vz, then it acts like a battery with capacity Vz. Okay. So it is the equivalence of the Zener diode. Next, while coming to the VI characteristics of the Zener diode, so here it is a forward current and it is a forward voltage. It is a reverse current and it is a reverse voltage VI. So it is a VI characteristics of a Zener diode. So here, if the Zener diode is forward biased, its characteristic is simply nothing but a parabolic kind of thing. It just replicates the VI characteristics of a normal p-n junction diode. But while coming to the reverse biased condition of the Zener diode, so in the reverse characteristics of a Zener diode, so it is a curve we are going to get here. That means at Vz, okay, if the reverse voltage is greater than the Zener breakdown voltage, then there is a sudden increase in current happens across the Zener diode. So before the Vz, there is a very minute amount of current flows through the Zener diode that is in the range of microamperes. But after crossing the Vz, there is a sudden increase in current takes place through the Zener diode. So it is called as a breakdown voltage. Why we are calling this one as a breakdown voltage? Because if we keep on increasing the reverse biasing voltage of a Zener diode at one particular voltage, that is called breakdown voltage. Okay, at that voltage, all the covalent bonds present, not all, almost most of the covalent bonds in the Zener diode starts breaking down. Whenever the covalent bonds breaks down, then there is a huge release of free electrons will takes place that leads to sudden increase in current across the Zener diode. It is a situation what happens at the breakdown voltage, and why we are calling breakdown voltage, because at that reverse biasing voltage the maximum number of covalent bonds are going to be breakdown and huge number of free electrons are going to be released, so that there is a sudden increase in current takes place across the and after the Zener breakdown voltage. Next, so from here to here we can say that the Zener diode is in off state. Why? Because very minute amount of current is flowing in this state, and while coming to this point we can say that the Zener diode, okay, from here to here we can say that the Zener diode is in on state, okay, and here the Zener diode is in the off state from here to here. Okay, how we are saying means here very minute amount of current is flowing within the range of microamperes up to the Vz. That's how we can say that the Zener diode is an off state, and just after the Vz, okay, so from here to here the Zener diode can be said as it is in the on state. Okay, so now at this point we can say that it is a I minimum. This point I am taking as a I minimum. That means the minimum amount of current is flowing through the diode when the Zener diode is in on state. Okay, and I can say it is the I maximum. That means maximum amount of current that can be tolerable by the Zener diode. Okay, so both these two are important, I minimum and I maximum. So I can say that I minimum is in the microamperes of range and I maximum is in the milliamperes of range. Okay. I minimum is in microamperes of range and I maximum is in milliamperes of range. Okay. So it is a basic requirement that we have to understand to solve out this problem with the help of the minimum concept regarding the Zener diode. Okay. So now to continue into the solution of the Zener diode, just look my next video that is titled as Gate 2019 Analog Electronics, question number 38 CONT. Nothing but continuation of this video. Okay. Thank you. Please subscribe my channel